we are going to learn the second order partial differential equations. Next, we take up second order linear PDEs. We see a few examples of second order linear PDEs. Next, we classify the linear PDEs. Later on, we take up the heat equation and we derive the heat equation in this lecture. What is a second order PDE? A second order partial differential equation is a PDE that involves the second order partial derivative terms r, s or t in the equation. Here small r equals dou square z by dou x square, s equals dou square z by dou x dou y, t equals dou square z by dou y square. The dependent variable z equals f of x comma y depends on two independent variables x and y. Geometrically, z equals f of x comma y represents a surface in the three-dimensional space. The general form of a second order PDE can be written as phi of x comma y comma z comma p comma q comma r comma s comma t equals 0. In this equation, at least one of the second order partial derivative terms r, s or t must present. Let's see a few examples of second order PDEs. The first example is r minus t equals 0. Here r and t are second order derivatives. So r minus t equals 0 is an example of a second order PDE. Our second example is r plus s plus t equals 0. The third example is rt minus s square equals xyz. These three are examples of second order partial differential equations. Throughout our lecture, we take the following notation. We take u equals u of x comma t. This is a function of two variables x and t. U is a dependent variable and x and t are independent variables. In this notation, x denotes the space variable and t denotes time variable. Now we use the notation u suffix x for dou u by dou x. U sub t equals dou u by dou t. We use u sub xx to denote dou square u by dou x square. U sub tt denotes dou square u by dou t square, and the symbol u sub xt denotes dou square u by dou x dou t. We use these symbols throughout our lectures. In our lectures, the main concentration is on second order linear partial differential equations. We consider u equals u of x comma t. U is a dependent variable and it depends on two independent variables x and t. X is called a space variable and t is called time variable. Then the general form of a second order linear partial differential equation is given by the equation A u sub xx plus B u sub xt plus C u sub tt plus D u sub x plus E u sub t plus F u equals G. In this equation, the second order partial derivatives u sub xx, u sub xt and u sub tt are present. So this is a second order linear PDE. Here at least one of the coefficients A, B or C must be non-zero. Otherwise, the equation cannot be called as a second order PDE. Now, in this equation, the coefficients A, B, C, D, E and F are either constants or functions of x and t. Similarly, the function on the RHS G is also a function of x and t only. If we take L of u equals A u sub xx plus B u sub xt plus C u sub tt plus D u sub x plus E u sub t plus F u, then this second order linear PDE can be represented as L of u equals G. L is a partial differential operator. Now, if G equals 0, L of u equals 0, then the given second order linear PDE L of u equals 0 is called a homogeneous second order linear partial differential equation. If the function on the RHS G not equal to 0, then L of u equals G is called a non-homogeneous second order linear PDE. In this lecture, we classify second order linear PDEs into two types. First one is homogeneous linear PDE. Number two, non-homogeneous second order linear PDE. So far, we have classified second order linear PDEs into two types: homogeneous linear PDEs and non-homogeneous second order linear PDEs. Now, we are going to classify second order linear PDEs again. First, consider a second order linear PDE of the form A u sub xx plus B u sub xt plus C u sub tt plus D u sub x plus E u sub t plus F u equals G. Of course, we can also consider a homogeneous second order linear PDE of the form A uxx plus B uxt plus C utt plus D ux plus E ut plus F u equals 0. Now we classify the second order linear PDEs into three larger classes depending on the discriminant b square minus 4ac. We say that a second order linear PDE is hyperbolic if the discriminant b square minus 4ac is greater than 0. So, a second order linear PDE is said to be hyperbolic if the discriminant b square minus 4ac is positive. We say that a second order linear PDE AUXX plus BUXT plus C UTT plus D U sub X plus E U sub T plus FU equals 0. A parabolic linear equation if the discriminant b square minus 4ac equals 0. We say that a second order linear PDE is elliptic if the discriminant b square minus 4ac is negative or b square minus 4ac is less than 0. So, we can classify the second order linear PDEs into three types: hyperbolic, parabolic, and elliptic equations depending on the discriminant b square minus 4ac. Let's see some very important examples of our interest. The first example is a one-dimensional heat equation u sub t equals a square u sub xx. We can also write this equation as a square u sub xx minus u sub t equals 0. If we compare this equation with the general form a sub uxx plus b u sub xt plus c u sub tt plus d u sub x plus e u sub t plus capital F u equals 0, then we can see that capital A equals a square, capital B equals 0, C equals 0, capital D equals 0, E equals -1, F equals 0. To find the discriminant, we require only the values of capital A, comma capital B and capital C. In this example, capital A equals small a square, capital B equals 0 and C equals 0. If we find b square minus 4ac, then we get b square minus 4ac equals 0 for this one-dimensional heat equation. Since b square minus 4ac equals 0, this one-dimensional heat equation is a prototypical example of a large class of equations called parabolic equations. So, a one-dimensional heat equation comes under the category of parabolic PDEs. Our second example is a one-dimensional wave equation given by the PDE u sub tt equals a square u sub xx. It can also be written as a square u sub xx minus u sub tt equals 0. If we compare this equation with the general form auxx plus buxt plus cutt plus dux plus eut plus fu equals 0, we get capital A equals a square, capital B equals 0, C equals -1, we require these values to find the discriminant b square minus 4ac. For this equation, b square minus 4ac is positive because b value is 0, capital A value is a square and c value is -1. If we find b square minus 4ac, we get a square. Hence, b square minus 4ac greater than 0. So, this one-dimensional wave equation comes under hyperbolic PDEs. So, a one-dimensional wave equation is a prototypical example of a large class of equations called hyperbolic PDEs. Our next example is the Laplace equation. The Laplace equation is u sub xx plus u sub tt equals 0. Of course, we can write it as u sub xx plus u sub yy is equal 0 also. Here, y equals t. In this equation, both x and t are space variables. Instead of t, we can also take y. For this equation, the values of capital A, capital B and capital C are capital A equals 1, capital B equals 0 and capital C equals 1. If we find b square minus 4ac, we get -4, which is negative. So, the Laplace equation is a prototypical example of a large class of equations called elliptic PDEs. These three examples are very important in applications also. In our lecture, we mainly concentrate on heat equation and wave equation. In this lecture series, our main concentration is on two types of PDEs. Number 1, heat equation. Number 2, wave equation. These two are examples of second order linear PDEs. Let us see what is a one-dimensional heat equation. Consider a function u equals u of x comma t. U is a dependent variable and it depends on two independent variables x and t. X is a space variable and t is a time variable. Now, a one-dimensional heat equation is a second order linear PDE given by the equation u sub t equals a square u sub xx, or it can also be written as a square u sub xx equals u sub t, or a square uxx minus u sub t equals 0. This PDE is called a one-dimensional heat equation because here we have only one space variable x. So, this equation u sub t equals a square uxx is called a one-dimensional heat equation. It is also called a diffusion equation. The constant a square is called a diffusion constant. A square reminds us the need of a positive constant in this equation. U sub t equals a square uxx. This one-dimensional heat equation U sub t equals a square uxx represents the conduction of heat in a metal rod, or it represents the diffusion of gases. So it is a very important partial differential equation in applications. Let's consider our one-dimensional heat equation again. The one-dimensional heat equation is U sub t equals a square U sub xx. It can also be written as a square U sub xx minus U sub t equals 0. If we compare this equation with capital A U sub xx plus capital B U sub xt plus capital C U sub tt plus capital D U sub x plus capital E U sub t plus capital F U equals G, we obtain that capital A equals a square, capital B equals 0, capital C equals 0, capital D equals 0, capital E equals -1, capital F equals 0, and the RHS G equals 0. So this equation is of the second order linear PDE form. So this one-dimensional heat equation is a second order linear PDE. We have already observed that the value of the discriminant b square minus 4ac equals 0 for this equation. So this equation is a prototypical example of a large class of equations called parabolic PDEs. Now let's see why this one-dimensional heat equation is linear. Let's take L of u equals a square u sub xx minus u sub t. Here u sub xx equals dou square u by dou x square. U sub t equals dou u by dou t. Then this one-dimensional heat equation can be written as L of u equals 0. So this is a homogeneous second order linear PDE. Now let's find L of u plus v. L of u plus v equals a square times u plus v sub xx minus u plus v sub t. U plus v sub xx equals dou square by dou x square of u plus v. U plus v sub t equals dou by dou t of u plus v. If we expand this equation, we get L of u plus v equals a square u sub xx plus a square v sub xx minus u sub t minus v sub t, that equals a square u sub xx minus u sub t plus a square v sub xx minus v sub t. that equals L of U plus L of V. Hence, L of U plus V equals L of U plus L of V. Similarly, we can show that L of alpha U equals alpha times L of U, where alpha is a real number. Since the partial differential operator L satisfies these two properties, L of U plus V is equal to L of U plus L of V, and L of alpha U equals alpha LU, we say that L is a linear operator. So, our one-dimensional heat equation is a homogeneous linear PDE. So, we have shown that the one-dimensional heat equation is a linear second-order PDE. Now, we are going to derive a one-dimensional heat equation U sub T equals A square U sub XX. This equation is also called a diffusion equation. This PDE U sub T equals A square UXX represents the conduction of heat in metal rods, or it represents the diffusion of gases or diffusion of a perfume in a pipe. Now, we derive this one-dimensional diffusion equation or heat equation U sub T equals A square U sub XX. This equation is called one-dimensional because we have only one space variable x. T is the time variable. We have only one space variable x. So, we call this equation a one-dimensional diffusion equation or heat equation. The constant A square reminds us the necessity of a positive constant in this equation. Now, to derive this one-dimensional diffusion equation U sub T equals A square U sub XX, we consider a pipe which is very thin and infinitesimally long and placed along the x-axis. We suppose that the cross-sectional area of this pipe is very small. We suppose that the width of the pipe is also very small. The pipe is very thin, and suppose that it contains a perfume which is concentrated, or we can suppose that the pipe contains a gas like hydrogen sulfide. Now we derive this one-dimensional diffusion equation by taking these assumptions and a perfume with some concentration in the center of the pipe, which is placed horizontally along the x-axis. Now, to derive our one-dimensional diffusion equation, we take a concentrated perfume in our very small thin pipe with small cross-sectional area, and its width is also very small. This pipe is placed horizontally along the x-axis. I have already mentioned that this pipe has infinite length. Now, we take the symbol U equals U of x comma t to represent the concentration of the perfume or mass in this pipe. The units of this physical quantity U equals U of x comma t are mass per unit length. We denote the concentration of the perfume by using the symbol U equals U of x comma t with units mass per unit length. If we integrate this quantity, we get mass per length because the perfume or the mass in this pipe is evenly distributed. Now, we take two positions x and x plus delta x on this pipe, and the difference between these two positions is very small, that is delta x. The difference between x and x plus delta x is delta x, and it is very small. Now, the mass in this small volume is approximated by the quantity U sub t times delta x. Here U sub t equals dou u by dou t. Now we need to observe the change of the mass with time in this small portion of the pipe between the positions x and x plus delta x. Here U sub t times delta x equals f sub in minus f sub out. F sub in represents the inward flux of the mass in the pipe. F sub out represents the outward flux in the pipe. U sub t times delta x equals F in minus F out. Here we have to find out the inward flux and the outward flux separately, and we need to substitute them in this equation. The inward flux F sub in is directly proportional to U sub x. U sub x means dou u by dou x. Since F in is directly proportional to dou u by dou x, we have F in equals minus a square U sub x. Now, we have to find out the value of F sub out also. Because F sub in is directly proportional to U sub x, we have found that the flux in equals minus a square U sub x of x comma t. The constant a square is a proportionality constant. The minus sign is because the diffusion occurs from higher concentrations to lower concentrations. Conventionally, we take positive sign if it is from lower concentration to the higher concentration. Because the diffusion occurs from higher concentration to lower concentration, we take the negative sign. So, the inward flux F in equals minus a square ux of x comma t. Similarly, the outward flux F out equals minus a square ux of x plus delta x comma t. Now we have to substitute the values of inward flux and outward flux in the formula ut delta x equals F in minus F out. It gives us ut of x comma t times delta x equals minus a square ux of x comma t minus of minus a square ux of x plus delta x comma t, that equals minus a square ux of x comma t plus a square ux of x plus delta x comma t. After taking out a square, we obtain ut of x comma t times delta x equals a square times ux of x plus delta x comma t minus ux of x comma t. If we divide with delta x on both sides, we obtain u suffix t of x comma t equals a square times ux of x plus delta x comma t minus ux of x comma t upon delta x. Here u sub t equals dou u by dou t, u sub x equals dou u by dou x. We have obtained that u sub t of x comma t equals a square times ux of x plus delta x comma t minus ux of x comma t upon delta x. Now we have previously selected a small portion of the pipe between the positions x and x plus delta x. If we let delta x tends to 0, we get u sub t of x comma t equals a square times limit delta x tends to 0 ux of x plus delta x comma t minus ux of x comma t upon delta x. This formula limit delta x tends to 0 ux of x plus delta x comma t minus ux of x comma t upon delta x is nothing but the partial derivative of u sub x with respect to x. So we obtain u sub t of x comma t equals a square dou by dou x of u sub x. That implies u sub t of x comma t equals a square dou square u by dou x square. This can also be written as ut of x comma t equals a square u sub xx of x comma t, or simply ut equals a square uxx. This equation is our required one-dimensional diffusion equation. This equation is called one-dimensional heat equation also. In this current lecture, we have selected second order linear PDEs. I have classified the second order linear PDEs into three major classes, namely hyperbolic equations, parabolic PDEs, and elliptic PDEs. Next, I have taken a one-dimensional heat equation. We have derived the one-dimensional heat equation also, but I postponed the solution of that heat equation to the next lecture. For further queries, you can contact me through mail. Thanks for watching.